Okay, welcome back, everybody. I have a lot in store that I want to share with you guys today. I am gonna start talking about FEA. That is absolutely the new agenda from here to the end, but I have just a couple of very quick loose ends that I want to close, and I will not spend too much time on these things, but I want to just address a couple of last points. Just to close out the interferometry discussion, and I will keep this brief. This equation was front and center. This is the equation that I claim, if you fully understand it, would be all you would need to know to understand truly how interferometers work. Okay. Now, what I didn't go into a lot of depth on was that delta phi1 minus delta phi2. I showed you maybe one special case of that. Okay. I showed you the case where it was a normal displacement interferometer and the surface moved at time t1 from here to maybe here, okay? And then you had a u at time t2, and I showed you that if you were retrieving these laser beams, then there's a round trip difference in here, which was u2 minus u1, okay? And I showed you that that would be responsible for this change delta phi1 minus delta phi2. Okay, does that make sense? So I showed you that simple case. And I said, if that was a case, and that's a very common case, by the way, that's the case where people are measuring normal displacements, okay? Whether it's full field or pointwise. And the point I want to make before I close this whole module out is that the recipe to understanding anybody's interferometer, I don't care whose it is you need to read and think about the path length problem in their configuration. In this case, that path length problem is nothing but this phi1 minus phi2 is nothing but 2 pi over lambda times this 2 delta, where delta is this thing, okay? And then that just becomes 4 pi over lambda delta of t, where delta is now the gap changing in time. Okay? All right. So somebody else comes along and says, hey, I've got this new interferometer. At the end of the day, I claim that if the path length change that contributes to this phi1 minus phi2 in their interferometer, okay, I'm calling them delta phi1 minus delta phi2, I think there. Okay, I call them little deltas. It doesn't matter. It's just symbolism. Okay. If you look at their diagrams and say, what do you guys claim your interferometer measures? You just have to look at the path length problem that is making their interferometer unique, and then you'll find some other quantity that sits in the argument of their cosine that allows them to measure something else with their interferometer. So this is it. What I'm trying to say is every interferometer has a flavor, and let me show you a totally different flavor. Okay, skip ahead. We talked about this last time. I don't want to talk about the LDA anymore. Here's one, which this was a paper written in 1977 where these researchers wanted to know, hey, when we impact this plate into this plate, and then we have a skewed impact in our experiment where this plate strikes this plate, and they're very flat and they make a nice planar impact, there's going to be motion if this guy flies in with velocity v. If I'm probing the backside of this target, there's going to be a transverse component of motion and a normal component of motion, you see? And what they were after was, hey, we'd love to be able to measure the transverse one. This is pointwise measurements now. This is 1977. This is like using laser interferometry, okay? Even today with DIC, this is barely resolvable because of the time scale and the tiny displacements that are involved, okay? So what they realized was, oh, interesting, if you put this diffraction grating, if you could print a diffraction grating on the back of your target, diffraction gratings have this magical property that if you send in a laser beam normally to them, depending on the periodicity of this grating, D, let's call it, this diffraction grating sends out these incredibly brilliant specular beams along these directions, which are labeled as orders, okay? Gratings are magical, magical elements, okay? They take a laser beam and they break them into these beautiful myriad of sharply defined laser beams. What these guys realized was, hey, if we mix, let me use my cursor instead of running over there in front of the screen. Can you see? Yeah, you can see the cursor, right? So here's this specimen. Imagine this grating is here where my cursor sits, and it generates this diffraction order and this symmetric diffraction order, okay? Just like I'd sketched here. So we're focusing on this one and this one, okay? And I don't know what prompted them. I know these people. I mean, I've asked them how the story occurred, but I don't know what deep in Kim's mind. Kim was the graduate student, okay, who discovered this and then called his professor to the lab to come see it, okay? I don't know what motivated him, but he had some insight that said, I'll bet you if I mix this plus beam with this minus beam only, if I can steer them, and if you watch the ray paths, you can see that they're ultimately brought together. I'll try to follow it with my cursor. Here comes this beam. Let's follow this diffraction order. It comes all the way through this lens, through the middle of this lens, hits this mirror, comes to this beam splitter, goes to the photodiode. There's one, right? And then you follow the other one. Here's the other order. Through the lens, mirror, mirror, beam splitter, they mix. So he found a way to mix just these two together, okay? So remember I told you the flavor of your interferometer has to do with the very path lengths associated with the beams that you've decided to mix, right? What he discovered was that the signal he got on the oscilloscope, the interferometer signal now, is purely sensitive only to this motion and completely oblivious to the normal motion, okay? It's a fantastic interferometer if you're interested in measuring normal motion. These would be the details that one would begin to unravel, and you could, we're not going to study it in depth, but if you study that diagram I've created on the right, you can understand why it is that the relative path length change contained between this plus n order, I'm calling it plus n and minus n, because you could mix any pair, right? You could decide to mix the -2 and the +2 if you wanted, right? So I'm calling it the plus n minus n. If you look at their path length differences and you subtract them from each other, you can even see I'll move the cursor so you can watch, if I was to subtract this one minus this one, you notice you have a minus delta U1 and a minus delta U1 here, okay? Those then are going to add and then therefore cancel out, and then you're going to be left with only the U2 component here, okay? So the subtraction of those two is going to only leave you then with one component of motion. Okay. So then this is what the experiment looks like. And physically, this is what it looks like in the impact chamber, okay? Because you've got to position these mirrors to intercept these beams that are coming off the back of your target. So imagine this is the target, okay? And then you've got to position these mirrors in your impact chamber, and they're going to be demolished. These mirrors are going to be absolutely demolished when this experiment is over, because this is an impact, and out of that gun barrel, which you don't see, which is contained behind that back wall, is going to emerge a projectile which is going to strike this target, which is sitting here, okay, at a skewed angle. And upon impact, the little diffraction grating that is sitting in the center is diffracting these beams out to mirrors 1, 2, and 3. Now, there is a fourth mirror there. There's a purpose for that mirror. It's got nothing to do with the interferometer. It's just to monitor whether, as they increase temperature in this chamber, if the target wandered, they took that beam out into the room, and they were able to readjust the position of that target to maintain alignment, because this was a high temperature test, okay? Anyway, that's what it looks like. Here's what it looks like out on the optics table when you bring these beams out, right? So you bring these beams out and then you mix them. And here was a typical interferometer signal that you could get, which is purely, these are the wiggles that I talk about. These are the fringes that would be recorded on an oscilloscope, okay? And the period associated with this signal that is recorded according to the theory is half the pitch of this grating per fringe. So if this grating, if this diffraction grating that you printed on the back side had a pitch d between these ridges on the grating that give rise to these diffraction orders, every fringe you get out on your oscilloscope screen, according to the theory, means the surface moved in plane by half the pitch of your grating, okay? And if you have a grating, typically might have a frequency, a grating frequency might be something like 600 lines per millimeter. Okay, so the physical grating might have 600 of these grooves per millimeter, okay? Which means this spacing here is d equals 1/600 millimeter, okay? So that's what the little d is, the spacing between your grating lines. And then these are well defined by a formula, which is called the Bragg formula, n lambda by d. So the angle that these beams come out at is well predicted by this formula, okay? So that sets that. That's what happens in the target chamber. And your sensitivity then, your sensitivity of this interferometer, since it's d/2, say micron per fringe, that means your surface has moved by in-plane amount that much, it would be 1/1200 in this case, because you're getting to divide that by 2. So the sensitivity of this interferometer, sensitivity, meaning how many microns per fringe that you record of in-plane motion, would be d/2, and then that ends up being 1/1200 micron per fringe. Okay, so the pitch of the grating dictated that. And a whole slew of experiments have been conducted since that time. We even have a lab that I've helped create on this campus that still uses this technique today. And whereas in those days, the beams were open and you saw them on the optics table like this, today they're fully fiber optic. It actually takes away the beauty of the experiment, in my opinion, but the power that you get back by using fiber optics, containing all the light, forcing it into the fiber, processing it faster, those gains far outweigh the aesthetic beauty of setting up this experiment open beam in this way. Here's how it looks today. Well, this is a generic cartoon, so you really don't understand. Yeah, it doesn't really speak to how it is today, but these are just fiber optics now and fiber optic probes. Actually, you can see that in the figure, right? So there's a probe here in the impact chamber with a fiber optic coming out the back, and a probe here with a fiber optic. And then here's the normal probe. And by the way, I didn't say this, but this probe still collects the 0th order beam and gives you your normal motion simultaneously. So in this experiment, you've got one channel on the oscilloscope, which is giving you the TDI, the transverse displacement signal. And then on another channel of the oscilloscope, you've mixed this one in the classic way, the normal displacement way, okay? And then you're getting the normal component of motion associated, say that one, whereas this one might be U2, okay? So this allowed people to probe the high strain rate behavior of materials. There's no tensile testing machine in the world that can give you the stress strain curve. Okay, so ultimately this is what everybody wants, right? They want this stress strain curve of a material, say in shear, okay? And there's no tensile testing machine in the world that could give you 10 to the 5 or 10 to the 6 per second strains, okay? Tensile testing machines like the ADMET downstairs or Instrons give you like maybe the fastest ones 10 to the 1, okay, strain rates. The rate at which, imagine this huge hulking device is going to have to pull so quickly. So the impact generating this thing at high velocities shears the material that you're testing, which is sandwiched between these two plates. Okay, a very thin layer of interesting, unique material. And the shear that you subject it to in this test gives you outputs that are translated to stress. And that'll be the last thing I say. I think I had a formula here earlier. Yeah, those formulas, which I kind of skipped by. They say, and this would be a whole lecture unto itself, we don't have time to do this, sigma, the normal stress, is related to the Vx free surface. Fs stands for free surface. So this interferometer gives you velocity normal to the free surface, Vx free surface in that little box. So by measuring the velocity, you have access to the stress. And then the second one, Vy free surface, is your transverse. That's what the transverse displacement interferometer gives you, and that's giving you shear. So imagine you have a means now to test, and so you can imagine the applications of this in high-speed machining or ballistics, where you need to understand the behavior of metals at enormous strain rates. There's no way to come up with stress strain curves for modelers without doing these high strain rate tests using impact. So there is a gun in the sub-basement of Firestone. It's a powder gun, and it can achieve, that projectile emerges from the barrel at 1 kilometer per second. We've achieved that, okay? We can reach speeds of 1 kilometer per second. We don't shoot at 1 kilometer per second every day, oftentimes 500 meters per second, but it's achievable to that degree, and that gives you an indication. The national labs have guns that can go several kilometers per second, okay? Because they're testing things at the most extreme limits. And this technique has made its way into national labs like Sandia and Livermore, and there are people there who use this technique studying unique materials that are of importance to national security, say, and we don't get to see what they test other than to occasionally run into them at a conference. So the story was really neat. I know Kim, he was a graduate student. He was still struggling to develop his English, but as his professor often says, he got this phone call. And he says, I didn't get calls from the students in the lab very often in those days. So I knew, like, Kim wants to tell me something important, right? And, professor, please come to the lab now, as the story goes. And then Clifton shows up and sees the fringes on the screen, and then they convince themselves that it was a purely in-plane sensitivity. And that just opened up a whole plethora of experiments for that group for decades. Clifton is 85 today and still writing proposals. He doesn't stop. I worked in that lab from 88 to 96. I was the research engineer in this lab, so I know it like the back of my hand. And I worked with graduate students who came through this lab for years before I went off into private industry. So this particular experiment is near and dear to my heart. I'm going to switch subjects now because we need to shift. So that was just my way of kind of closing out interferometry to say that formula we derived was very generic, and it comes down to understanding the phi1 minus phi2 ingredient of anyone's interferometer. And every interferometer variant in the world has to plug in some phi1 minus phi2 that defines that interferometer's sensitivity.